start today was to with the bare bones stuff. So let me open up the README for this bare bones thing. Let's just remind ourselves as to what we have here. These reserved keywords or reserved words, right? Those are basically the instructions that you have available to you in this language. And as we discussed last time, doesn't it seem like there's some stuff missing? Right? So, what was missing? Arithmetic was basically missing, with the exception that it already had the ability to add one or subtract one from a given value. So that was increment and decrement, respectively. Okay, but other than that, there's no arithmetic instructions there. And we saw that we could actually, that's okay, we could build addition or subtraction. Um, or multiplication even out of what we do have here. Okay, so even though it's not strictly speaking a base part of the language, we can get it with other things out of the language. What else did we say was missing besides the arithmetic? Okay, loops. We've got a while loop, right? But it's in a certain form, right? While something is not zero is sort of the only loop construct that we have. Okay, so yes, the other loops like for loops or a while loop that depends on something different. Okay, we don't have that. We also don't have a do while loop. And then what else is missing in that? The else, right, or conditional expressions, right? So an if then or an if then else kind of construction. So let's actually think about how we could do an if then construction. And the only thing that we have to do it with is the while instruction, right? Because the while instruction is the only one that has any sort of decision-making power in it. The other ones just do something to a variable, like set it equal to 0 or add 1 or subtract 1, or copy it from one place to another, right? So only the while construction here is going to help us in any way, shape, or form. Okay, so let me make a new file. Okay, I'll call this conditional2 because the other class obviously did this. We did this exercise earlier. And what I want is something like the following. I want to be able to do okay. I want to be able to do something like this, right? Which is to say, if x is not 0, do something. Okay, and then the else, well, that's something that we could tack on. Okay, I'll leave that part as an exercise for you guys. Right? This is what I want to have, something that effectively does this. But the only thing I can build it out of is something like this. Okay, good. So I would want, obviously, to have do stuff here. And just for sake of demonstration, let me do the following. Let me initialize n to be 0. And where I have do stuff, let me just use adding 1 to n as my stuff to do. Now, what really could do stuff be? That could be 1,000 instructions. Okay, it could be just no instructions. It could be one instruction. So just to have something there, let me just put add 1 to n as my stuff. Okay. Okay. So if I were to run this right this instant, okay, what would happen? Well, it kind of depends, right? Because what do I have to supply to run this program? A value of x. Okay. Well, what values of x am I permitted to supply? I can either make it 0 or not 0, right? Could be a 0 or it could be something different. If I supply 0 to it, what's going to happen? It's going to just terminate. Nothing would happen, essentially. Okay, so if I supply 0 to this program, what would be the value of x and n when the program terminates? They'd both be 0. Okay, do you guys see that? Yes? Okay, what about if I supplied x is 5? It's going to go on forever because did I ever change x inside my loop body? I changed n, but not x. Okay, now would you guys agree that that's a bad thing for this to loop on forever? Because how many times do I want it to increment in? Precisely once, right? So I need to add an instruction here to make sure that I don't end up looping forever. Any brilliant ideas? Set x equal to 0, right? Because then if I do, when I come back and check, is x equal to 0? I'll be like, yep, it is, so I won't loop. Yeah? How do I set x equal to 0 in this language? I can't do init x equal to 0. You can only do that at the top of the program. Clear, exactly. So I'll just clear it. Okay? Clear is, in this language, just sets the value of it to be 0. Okay, so bam, it's gone. Okay, is this going to do our job? Right? So let's think through it again. What about if I supply this x equals 0? Will anything happen? No, just like before. Okay, so that part's still okay. But what about if I supplied x equals 5? Well, all right, n is 0. Is x not 0? Yep, okay, increment in, so what's in now? 1. Clear x, so what's x now? All right, is x not 0? Nope. So move on past the loop, and since there's no more code, then the program terminates. I'm done. Well, there we go, right? We built an if statement. That's pretty cool, right? That's cute. What do you guys think? Is this kind of clever? Yeah? Okay, so your exercise is to then figure out how to tack on an else to this, okay, which will require some thought, but this wasn't too bad, though, was it? Yeah, okay. Let's double check it with our actual interpreter and make sure it does what I said it did. So what was this? Bare bones. I need to set x equal to something. All right, so if I set it equal to 0, what happens? Everything terminates and everything's still 0. Okay, no big deal. What about if I set it to something that's non-zero, like 5? Then what's in? 1, not 0. So that meant that the loop body got executed precisely once here, which is what we wanted. Okay, that's kind of cool. Yeah. All right. So let me. Okay. So any questions about that? Because we're gonna move on to the to a very similar program that looks sort of like that, but then talk about this big question, this halting problem question. Okay. All right. So is that good on the bare bones stuff for right now? Okay. All right. So let me write a new program. And I'll call this Y machine for reasons that'll become clear later. Okay, so looking at this program, this is a program, and I would need to supply a number to this program as input, the number Y, okay? And as before, what could Y be? It could be 0 or it could be something else. What would happen if I supplied 0 to this program for Y? Would it terminate? Yes, okay? What would happen if I supplied something that was non-zero to this program for Y? Mm. Okay, good point. So the comment was it would either go up to 0 and terminate, but, and this is maybe something I forgot to mention, bare bones only allows you to have positive values or 0, so no negatives. Okay, so if there's no negatives permitted, then it would go on forever. Okay, because if 5, for example, is 5, 0, no. So add 1 to 5, and I now have 6. Is that 0? Nope. And so would this ever terminate? No. Okay. Now, there's really two ways to answer that question, which is to say, on a particular computer, so on my Raspberry Pi here, is there a maximum number that you can add up to? There is, okay? Because my computer has finitely much memory, eventually I would hit some gigantic number, and I would overflow and wrap back around to the negatives and stuff, okay? So in terms of this particular implementation, this probably would eventually terminate, but it would go on for so long that, we'd all be dead by the time it finished. Exactly. That's a good way to put it. We would terminate before it does. Okay. Um, but let's think about the Turing machine thing, right? Was there any sort of limitation on the Turing machine in terms of how much tape it had available to it? No, we never put a limit on that. So it was the idea of a Turing machine was that if it terminates in finitely much time, great, but it could keep running. And if we sort of theoretically imagine infinite tape, well, it could keep running forever. Okay. So if I supply this program with 0, and so let me do that. Oh, and I need to specify y equals 0. Then it terminates. But if I give it a y that's not 0, then what's happening? It's fed the initial value of the variable y as 1, but why hasn't it told me the final value of the variable? Because it's still running, okay? And in fact, you can see that up here, my processor activity monitor is going nuts, right? It's going up to 1/4 because this thing has 4 cores in it. And so it's just running, right? And by now, I'm sure that y is in the thousands or something. Okay, I don't have anywhere to know because there's no print function in this language, but it's just running and running and running. Okay, is this ever going to terminate? No. But how do I know that? How do we know that this program wouldn't terminate? Well, because we looked at the code and we just used our damn heads, right? But strictly speaking, then, let's say you didn't see the code. Would you know that this is or is not going to terminate? No, all you know is that it hasn't terminated yet. So how do I know that it's not going to terminate next week or next year? I don't, right? Unless I actually get to look at the code, okay? All right, so do you guys accept that we looked at this code and were able to determine for a given input, a value of y, whether it would or would not terminate? Yes, we were able to do that. Okay, congratulations. You guys are Turing machines, right? So could we theoretically come up with a program that would be able to look at this code and tell us for a given value of y whether or not it would or would not terminate? Okay, how do I know that such a program would exist? Well, because you guys as humans just did it, right? If you could make this decision by analyzing the code, then a computer program should be able to also, okay? Okay, but let's change the question a little bit, okay? And let me maybe go on a brief historical interlude here, okay? So let's go back to, um, the what we're talking about is this halting problem, right? Basically, can we, for any computer program, determine whether or not it would halt after some amount of time, or be able to know whether or not it would go on forever? For a particular program, like the one that we just wrote, could we look at it and make that determination pretty easily? Yeah. Okay, and now this is not certainly a super complicated program, but could we imagine even if the program had 1,000 lines of code, might take us a little while, but could we go through it and figure out whether or not it's going to halt or not? Yeah, we could probably do it. Again, might take a while. We might need a special delivery of some extra chicken tenders and a couple of cases of bangs, or Byron to bring over a bunch of Lotus or whatever it is that you guys drink. What does that stuff taste like anyway? The Lotus drinks at the brew? No? That's kind of scary because Red Bull already is sort of artificially flavored. So it's like, yeah, no kidding. Okay, well, anyway. Um, okay, so let's kind of go on a historical interlude here. The halting problem is very, very much related to this decision problem. And the decision problem, as we'll sort of talk about, and we'll watch a video towards the end of class. Um, I think when I mentioned Turing's paper, when we started talking about this last week, I mentioned the Entscheidungs problem, right? That's German for decision problem. Okay, so um, mathematicians in the early part of the 20th century, sort of right around the turn of the century, were, amongst other things, very concerned with what are you actually able to do with mathematics, and is there a limit somehow on what math and logic could eventually do? Okay, not to say that. I mean, there was also thought about this in the 19th century. Um, Okay, but to give you a good example as to sort of how this, or a way that this sort of question came up, is talk about, well, let me switch over to the iPad and talk about a guy named Euclid. Has anybody ever heard of this guy? Who's Euclid? Yep, ancient Greek mathematician. Roughly when did he live? Yeah, 300 BC, roughly, was sort of when he was active and flourishing. We know very little about him in terms of like biographical information. Now, part of that is because, well, it was several thousand years ago, right? And he lived and worked in Alexandria in Egypt, which at the time was controlled by a Greek dynasty. So that happened because, well, let's go through, 100 years of sort of ancient history in 30 seconds. So there was this guy, you may have heard of him. His name is Alexander. He was pretty great, right? What did Alexander do? He conquered a whole lot of territory, right? He was Macedonian, so northern part of what's now Greece, right? Conquered lots and lots of territory, going as far into India and what's now India and Pakistan, right? That kind of region. Also conquered Egypt. Never conquered Sparta, believe it or not. Um, maybe shocker why. Yeah, but he goes and conquers just huge swaths of territory. And then he just suddenly dies in Babylon when he's, in his 30s, essentially. So he's effectively conquered the known world or much of it. And then he just dies. Well, he had a bunch of generals, right? And what happened after he died? Yeah, they probably went to war against each other to fight over what was left of the territory. And essentially, what happened is they carved it up, and everybody got a piece. Okay. Well, Ptolemy was one of the generals, and he was smart. I think he's like, "I'll take Egypt," and he went over to Egypt and didn't engage in the fighting with everybody else. He's just like, "I'm going to take my ball and I'm going home." Okay. Um, and so that dynasty established in Egypt. One of his descendants uh, basically made Alexandria, and there were a lot of cities that were founded in the wake of Alexander's conquest that are named Alexandria. In fact, there's one of them that's called Alexandria the Furthest because it was like way out in the boondocks. Okay. Anyway, so he founds Alexandria, and the Ptolemaic dynasty really supported it as a center of learning and a center of active research, right? And so it became an intellectual hub of the ancient Mediterranean world. Euclid, like a number of mathematicians, lived and worked there. Okay, what is Euclid known for? right? He's a mathematician, yes, but what did he do? Yeah, in some respects, he wrote what was considered what we could call the first geometry textbook, or it's the first one we certainly know about its existence. Okay, it was called The Elements, and even until say 150 years ago, like when you guys took geometry in high school, right? What book did you use? Some book written by some textbook company that charged your school districts way too much money, right, for it, and it had a bunch of pictures and flowery crap and was like super thick uh, and silly, right? Well, 150 years ago, you'd just be given a copy of Euclid, right? That's it, right? That it's all there. Okay, so he wrote this book called The Elements, and at the beginning of the book, he makes some definitions. Okay, what is a line? What is a point? What is a parallelogram? What do all these words mean? Okay, fine. And he also has some postulates. Okay, which is about what are you allowed to do in sort of a geometric system. And the fifth postulate that he gives, I'm not going to state it the way Euclid did because the way he stated it's kind of confusing. So I'll state something that's equivalent to it, but not actually what Euclid said. So just bear with me there. All right, so let me draw a line and let me draw a point. Okay, so a straight line and a point that's not on that line. How many parallel lines can I draw through the point that are parallel to the line? Precisely one, right? And what would it look like? Well, you guys aren't morons. It'd look something like this. There's exactly one parallel. Okay, so perfectly reasonable, yes? But this fifth postulate really bothered mathematicians of the day in the sense that they thought, do we really need to assume that from the beginning, or could we prove it from all the other things that are also being assumed? Like, do we really need to have this in the list of assumptions, or does it follow from the other assumptions that we've already made? Okay. And so they puzzled over this. And what do you think the answer is? What do you guys think? Well, turns out that any effort to prove that from the other assumptions in Euclid is doomed to failure. Okay. And the reason is that this postulate, this parallel postulate, is somehow independent from the rest of them. Okay. And here's how we can know that it's independent. And this is where really the Greeks they should have noticed this, but for some reason they didn't. This is where it came in the 19th century, for example. Let me draw a sphere. Okay. I'm not an artist, but bear with me. Okay. Will you guys humor me that that's a pretty good looking sphere there? Right? Yeah. And actually, this reminds me, sort of for humor for a moment. How many of you guys have seen the video on YouTube or the original Flash comic called "The End of the World"? No. Okay, I'll send you a link to it. It's funny. Okay, so I've got a pretty sweet sphere here, right? What is a straight line on a sphere? Well, that's kind of a weird question, right? And so we'll make a definition that a straight line on a sphere is a segment of what's called a great circle. Okay. Now, an example of great circle is the equator. Okay. So think about this sphere as, for example, being the Earth. Okay. The Earth is mostly spherical. It's kind of bulgy at the equator, much like Liam's mom. But no. Yeah. Yeah. Okay. So anyway, I had to get a good Yo Mama joke in there somewhere, right? Yeah. Um, all right. So the Earth actually bulges a little bit at the equator, and that's for a couple reasons. One, because it's not perfectly solid, right? It's kind of mushy, especially in the middle because it's hot. And also because it's rotating. Okay. But anyway, let's just for the moment pretend that the Earth is a perfect sphere. So the equator is a great circle. It's a circle whose radius is exactly the same as that of the sphere. Okay. Can you think of other great circles on the Earth? Okay. All of the lines of longitude are great circles. Okay. And what's true about every line of longitude? They all go through both the North and the South Pole. Yes? Okay. What about the latitude lines? Only one of them is a great circle, and it's the equator. Okay. The one corresponding to 0 latitude. All the other ones, as you kind of go, because what's true about the latitude lines as you go up the sphere, they get smaller, right? And so they're circles, yes, but they're not great circles. Okay. All right. So if we define straight line as being a great circle or segment of a great circle, if I take a line and a point not on that line, say for example that green dot, how many lines can I draw through that green dot that are parallel to the orange circle? Well, that's asking, can I draw a great circle through the green dot that never intersects the orange circle? And you guys can look at it and say, no, you can't. Right? Can you imagine? Right? Imagine you did. What would have to be true about the thing? It would have to go back around, right? And so it would intersect the orange circle someplace, actually at two places. Okay. All right. So what does that mean? Are there any parallels to the orange circle? No. Okay. So on the sphere, there are no parallel lines. Okay. And this maybe begs the question, well, what is the definition of parallel in the first place? What does it mean for two lines to be parallel? They never intersect. So if you have two lines that do intersect, they are not parallel. Okay, well, bam, spherical geometry, you start with a different assumption about this parallel postulate, and you get a different geometric system that works perfectly well. It's perfectly consistent. Okay, and so how many parallels were there in Euclid's case? Precisely one. How many parallels were there in the spherical case? 0. Okay. And what's the other option for 1 or 0 in mathematics? Well, what about infinitely many? Right? It's like Oprah Winfrey's parallel postulate. You get a parallel and you get a parallel. Right? So there is a geometric system. It's called the hyperbolic system, where there are infinitely many parallels. And that one's bonkers. It's very hard to visualize. Okay. But people figured this out in the 19th century that, oh, you could take Euclid's postulates and just change the parallel postulate and get a perfectly valid geometry. Okay. So somehow the question of trying to say, is it true or not that Euclid's uh, parallel postulate could be proved by the other ones was doomed to failure from the get-go. Okay. And so what this sort of spawned is a bigger question as to, given a logical system, are there things that it is unable to do? Yes or no, right? Okay. And sort of the equivalent or related question for our purposes is this question of what's called the halting problem. Okay. So given a program and an input for that program, can I determine whether or not that program halts? Okay, if I give you a specific program, like here's the code, bro, could you determine that? Probably. Okay, we just did for an example program, right? We wrote a program that under some inputs terminated and other inputs did not. Okay. Okay, so we might be able to do this for an arbitrary program that gets handed to us that we're able to sit there and think with. Okay, but let's change the question a little bit. Is it possible to do this for any program? Okay, and let's change the question slightly more. Well, if we as humans could determine it, wouldn't that mean that we could write a computer program that could do that for us instead? Okay, so what I want to know is there a program that if I give it another program and an input for that second program, it can look at it and determine whether or not that program halts? That's what we're asking. Does this thing exist? Okay, all right, so we're going to play a trick that we do very often in mathematics and in logic, which is to do what's called a proof by contradiction. Now, what I'd like to argue, and what the point of today's discussion is to argue that no such program can exist. Okay, so there is no magic program that can determine for any program whether or not that thing halts. Okay, so how could I disprove the existence of such a thing? Well, let's assume that such a program does exist. Okay, and if we do, and we play with it a little bit, and we find ourselves in logical bullshit land, then what do we need? What do we have to conclude? That the assumption that we made from the get-go was itself bullshit, and therefore such a program cannot exist. Okay, now I know that's kind of a logical head spinner, okay, but that's sort of the idea here, right? Let's assume that such a program exists, and then kind of go forward with it to see what conclusions could we draw, and we're going to find ourselves into a trap. Okay, that's the idea. Okay, so in order to explain this better, I'm actually going to let somebody else explain it. If the computer will cooperate and I can find where the heck my mouse is, there it is. Okay, so how many of you guys have ever heard about computer file or number file? No? Okay, so these are two kind of pretty popular YouTube channels that do pretty nice informative videos about mathematics and about computing. Sometimes they're interviewing famous mathematicians or computer scientists. Sometimes they're doing stories about certain concepts. And so what we're going to do, and I'll quit the stream because I don't want to stream a video of YouTube to YouTube. That's kind of silly, right? Is to look at one of their videos on the halting problem, and then we'll kind of talk about it a little bit after it finishes. Okay, does that make sense? All right, so I'm going to quit the stream right here, but we're about to watch that top video on the screen.